Hi guys, so today I was thinking we could do chapter 8 so you guys could have plenty of time to study for the test. So I think the test is gonna be in either on 1 or 2 weeks, but it is quite nice because it's only gonna go over chapter 7 or 8. It's chapter 7 and 8, and then for the final I think it's gonna go over chapter 9 and a little bit of chapter 10, but nothing crazy. Chapter 10, I would say radicals, and chapter 9 on the aspect of reactions with alkynes, which are carbon-carbon triple bonds. And so for preparation for the exam number 3, I'm possibly gonna do a video afterwards going over my exam from the previous semester. And of course, if you guys have any suggestions, maybe going over a few more like reactions with alkenes, or maybe from content from chapter 7, just let me know and I can do that. So just a heads up before we get started, if you hear any hissing or any barking, I just got a new puppy like 1 or 2 weeks ago. So he's fighting with my cat a lot. So then you're probably gonna hear maybe a little fighting on the background, but nothing crazy. So, no, keeping that in mind, I guess we can get started with chapter 8 content. So, chapter 8 alkene reactions. So, we have addition reactions. So, in the previous chapter, we learned to make alkenes via elimination reactions. In this chapter, we will look at addition reactions, which are reactions dealing with alkenes. And we know alkenes are double bonded carbon-carbon bonds. This is when a double carbon-carbon bond is broken and we add two groups across that double group. So for example, that's why I circled. That's why I circled, that we break that double bond, and then addition of X and Y. And we add X on one side, then we add Y on the other side. So we're gonna see some common type of addition reactions. We're gonna see a reaction called hydrohalogenation, in which we're gonna add, a hydrogen, of course, and then a halogen, which we know that a halogen is a chlorine or bromine or iodine. Or we're gonna do reactions called hydration, in which we're gonna add a hydrogen or an OH. Or we're gonna do reaction called hydrogenation, in which we just add one H on one side, one hydrogen on one side, and one hydrogen on the other. Or we're gonna do halogenation, in which we add a halogen on one side and another halogen on another side. Or a halohydrogen formation, in which we add an OH and then a halogen on the other side. Or the hydroxylation, in which we add an OH on one side and an OH on one other side. So I feel like this is like a nice heads up, or like a nice summary. Of course, there's much more to know about each reaction, but I want you to, maybe go back to this part of the video and be like, oh, what's a hydrohalogenation? What's hydration? I don't feel like you really need to know like the names, hydrohalogenation. What's more important, I feel like, is like the reagent. Like for example, you're giving an alkene, and then you, with a specific reagent, what product you can get out of it. I feel like that's the most important thing, rather than knowing what's the specific name for that reaction. So, types of addition reactions. So, as we know, double bonds can work as nucleophiles, but they can also work as weak bases. So I just gave an example of how double bond can work as a base. As a base, just taking, a hydrogen, but it can also act as a nucleophile. A nucleophile, what it does, a nucleophile normally it reacts with an electrophile. So then we always start every chapter with a little bit nomenclature of alkenes. So we have to remember a little bit of IUPAC rules. So then we already know the basic rules, like we have to identify the parent chain, which is the longest consequential chain. We then have to identify the substituents, which are the things that hang from the parent chain. Then we assign the location, the lowest carbon to each substituent, and then we arrange the substituents alphabetically. So alkenes, carbon-carbon double bonds, they use the same rules, but there's a few changes. So things to consider when we name alkenes. For example, there's this suffix which is aim for alkenes. Like for example, we have things like there's a suffix aimed for alkenes, so we have like butane, pentane, hexane, and all of those they are all of those they are carbon-carbon single bonds. There's no like double bonds in any of them. But for example, if we use the suffix "-ine", it's for alkenes. So for example, in here we have a pentene, which is compared with a pentane. So you can see that a pentane doesn't have any double bonds, but a pentane at some point it includes a double bond. I told you there's gonna be some fighting here. So for example, if we have an alkene, which is the longest continuous chain that contains the alkene as our parent chain. So then, for example, if we are giving just in here, we are just giving a basic chain, right? It doesn't contain any double bonds, as we can see. So we use the rules that we've known so far. We just try to find the longest sequential chain. So for example, in here we have 1, 2, 3, 4, 5, 6, 7, 8. So here we have 8, but in here we have 1, 2, 3, 4, 5, 6, 7. So in here we have 7, and then in here we have 8. So this is why this one is our parent chain. But instead, in here we will have 1, 2, 3, 4, 5, 6, 7, 8. In this I will have 8, but then 1, 2, 3, 4, 5, 6, 7. In here we will have 7. But you can see that our parent chain ends up in a heptene, because the thing is that when we have a double bond, a double bond has a higher priority than a single bond, carbon-carbon. So then no matter if we have like a longer sequential like carbon-carbon single bonded, the one with higher priority is gonna be the longest chain that includes that double bond. That same knowledge goes if we have like a carbon-carbon triple bond, for example. We will prefer the longest chain that contains that triple bond over one that's double bonded, or over one that is just single bonded. So there's more things to consider. So when assigning carbon numbers to the substituents, the alkene receives the lowest possible number no matter the other substituents. So for example, in here we have the correct and the incorrect way. So then we know that we want to assign the substituents the lowest number possible. So you'll be like, oh, okay, so if I started to count, in here our first substituent will have 2. and then the second one will be 3, and you can see that in here we have 2 with 3, so you will be like, okay, so I have 2, 3, 3, and then in here I have 2, 3, and then I have 5. So you'll be like, oh, this one wins because this one has, the lowest number. But the thing is that we want our alkene or alkyne to have the lowest number possible. So then, since we wanted to have the lowest number possible, we technically forget about the other substituents, and then we just focus on that alkene, on giving that alkene the lowest number possible. So that's why this is the correct way of naming it. And the position of the alkene is shown before naming parent chain. So then, organic chemistry is very subjective. So for example, in here it's just there's different ways of naming it. Of course, they still follow the parent chain, that your longest chain that contains that double bond is gonna be the parent chain, and the things that hang from it are gonna be your substituents and where's that located. But you can see that they make a little exception for you on showing where your double bond starts. So for example, in here they put it before the parent chain, but in here they put it in between. It says hep, which is your parent chain name, but in between it before that suffix for the alkene, they put a number 2 in between. So for example, you could either call it 2-heptene or you could call it hep2ene. But that's up to you. I personally like this one better than the other one, but you can see that on a test or on a quiz, for example. It wouldn't really matter as long as you're able to properly name it, properly assign the number of the number of substituents, or the substituents, what's your parent chain. You can do any of them. You can either put hep2ene or you can do 2-heptene. Knowing that, we can practice a little bit naming our parent chain. So on naming our alkenes. So we're gonna practice a little bit together, and then we're gonna do some practice problems as always. Okay, so now we're just gonna try to find our longest chain. So then let's see, in here we got 1, 2, 3, 4, 5, 6, 7, 8. So here I got 8. So here 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. So I feel I think we kind of got a grasp on which one's our longest chain. So obviously this one is not gonna be our longest chain because we have a chain that's the longest chain right now is 8. And also it's because since we have the presence of a double bond, we want our parent chain to contain that double bond. So then we're gonna try to find the longest sequential chain that contains a double bond. So then we can either pick this one, 1, 2, 3, 4, 5, 6, 7, 8, or we can pick this one because they end up being the same overall. Okay, so keeping that in mind, we can actually now try to assign our substituents. So then let me erase this so we don't get confused. And then, so we can assign our substituents now. So this one's 1, 2, 3, 4, 5. Okay, so I know this one's a metal. I know this one's a metal. I know this one's a metal. I know the 2 carbons, ethyl. Okay, so then I can assign numbers. So we want our alkene to have the lowest number possible. So then if you think about it, if I start from here, 1, 2, 3, and 4, it will be the same if I were to start in here, 1, 2, 3, 4. So now it's when it takes into account the other substituents. So then, for example, in here, my first and second substituent, my first substituent will have position number 2, and in here my first substituent will also have position number 2, but then my second substituent will also have position number 2. So then I would prefer this side over the other one that I shown previously. So then I would do 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I feel like we're kind of ready. I do have to name my parent chain though. So then, since we have an 8 carbon sequential chain that contains an carbon, is gonna be, so then we know that we have oct, but since it contains a double bond, it's gonna be called octene. So you can technically think about it. Okay, I know that an carbon chain that is 8 carbons, it's called octane, but that's when it's an alkane. So then it's double bonded, so it's gonna be called octene. Okay, let's see. Okay, so then we have an octene parent chain. Okay, so then now we can technically name them alphabetically. Oh yeah, also with something else that we have to keep in mind is that when we do when we're naming what's it called, when we're naming alkenes, we most of the time say assign priority groups. Like for example, we say at the front of the name whether it's E or Z, So then we do have to we do have to take that into account. So then let's see. Let's see. I do have a problem with this one. So then E is for trans. And then C is for cis. I don't know why, but I do better assigning trans like with the name, I feel more comfortable assigning trans and cis rather than assigning like, you know, E or C. It is kind of complicated at the beginning, to be honest. So then let's see, now we can do alphabetically. So then we're gonna have, you know, ethyl is gonna be assigned as E, methyl is assigned as M. So it is quite nice because E has, you know, in the alphabet it has priority over M. So then we can start with E. We're gonna do, we have a 4 and a 5 ethyl, so then we're gonna do 4,5 diethyl. And then our other substituent is methyl, and we have 3 methyls, so then we're gonna do, we have 2,2,7, so then we have 3, so it's gonna be trimethyl. And then our double bond starts at 4, so then we have 4 and then octene. And then we say that we assign our priority. So then, for example, if we have to compare this one and this one, the one that has higher priority is going to be this side. And then if we have to compare this one or this one, the one that has higher priority is going to be this side. So then if you think about it, they're going to have that E relationship, or you can say trans, and then we normally assign that up front, so we're going to put that in here. So our answer should be E slash 4,5 slash diethyl slash 2,2,7 trimethyl for octene. So those are some things to consider mainly. I feel like most people, they forget to assign whether it's E or C. And don't feel bad if sometimes you have to look at your notes back to see what is E and what is C, because I definitely did right now. So we can try it on our own now. And I was quite nice with you guys. I gave you guys a little bit of an easier try it on your own. Okay, perfect. So I guess we can do this one together now. So now we're gonna have to find our longest sequential carbon-carbon chain. So then here you have 1, 2, 3, 4, 5, 6, or we can do 1, 2, 3, 4, 5. So we want our longest sequential chain that contains the double bonds. So luckily, our carbon-carbon chain with the 6, it contains our carbon double bond, so we can use that one. And then we can circle our substituents, which is only 1, and then it's a metal. So after that, we can number our substituents. We want our alkene to have the lowest number possible. So if we start from here, 1, 2, 3. If we start from here, like 1, 2, 3, 4. But then if we start from here, we'll get 1, 2, 3. And both of our substituents, they will get position number 3. So therefore, we will prefer this side over the other one. So we can do 1, 2, 3, 4, 5, 6. Okay, perfect. So knowing that, we can see if we can assign priority. And luckily we can, because in here, you know, we have like a hidden hydrogen right there. So then we can technically assign priority, keeping in mind that E is for trans and C is for cis. So then if I were just to look at this one, there's so many things to consider. So if I were to look at priority groups, my left side, if I was comparing this side and this side, this side will have higher priority than down here. And then if I was to look at my right side, you already know that a carbon that a carbon chain has a higher priority than a hydrogen. Therefore, my configuration will be E for this one. Okay, perfect. So knowing that, we can assign our parent chain also. So then we have a 6. We already know that a carbon-carbon bond that is 6 is gonna be hexane, right? But we're dealing with a carbon-carbon double bond, so instead it's gonna be called hexene. So then, okay, perfect. So we first start putting our configuration. So this one's E, as we said. And then luckily we only have one priority group. Not one. We only have one substituent. So it's gonna be 3 methyl. And then we have to remember to say the position of our double bond. So it's gonna be next to our parent chain. Like when we say the name of our parent chain, so we're gonna put that it begins at carbon 3. So then we have 3 and then hexene. Okay, so then let's see. In here we can do 1, 2, 3, 4, 5. And we can also do it like this, 1, 2, 3, 4, 5. We could technically 1, 2, 3, 4, 5. But the thing is that we want our parent chain to contain the double bond. So then here we have 1, 2, 3, 4, 5. So then carbon-carbon bond that is 5 is gonna be called pentane. But since we're dealing with a double bond, it's gonna be called pentene. Then after that, we can see the things that are hanging off from it are substituents. So then we have a methyl and then an ethyl. Okay, perfect. Okay, methyl, ethyl, we have this. We can assign our substituent number. So then we have 1, 2. So then in this case, we want and in any case, we want our alkene to hold the lowest substituent number. So it's gonna be 1, 2. And in the other side, it contains 3. Therefore, we're gonna prefer this side over the other one. So we're gonna have 1, 2, 3, 4, 5. So then that will be the right way. And then what else we have missing? We have to see whether we can do priority groups, and we can. So then we have an H. So then if we analyze this side, the one that has a higher priority is gonna be a carbon. A CH3 has a higher priority than a hydrogen, or a carbon has a higher priority than a hydrogen. So then this one has higher priority. And then if I was to analyze this side, the one that's gonna have a higher priority, oops, let me make that circle. If I was to analyze this side, the one that's gonna have priority is gonna be this one, just because in here I'm comparing a carbon. I'm comparing carbon, hydrogen, hydrogen, while in here I'm comparing a carbon, carbon, hydrogen. Therefore this one has higher priority. I mean, I wanted to erase that circle, but seems like I can't. But let's see, if we think about this one, it's gonna be on this side, and then this one's gonna be on this side. Therefore, I feel like we're gonna have a E relationship or a trans relationship. So we can begin naming it. We're gonna have E. So then we have methyl and ethyl. So ethyl is gonna have if we arrange it alphabetically, ethyl is gonna come first, and then we only have one ethyl substituent. Oops. We only have one ethyl substituent, which is in position number 3, so then we can do 3 ethyl. And then we only have one methyl substituent, which is on carbon number 4, and it's gonna be 4 methyl. And then we have to say next to the parent chain name. Since we don't have any more substituents, normally your parent chain name comes in, but we have to first say the position of where that carbon-carbon starts, like the double bond carbon-carbon starts. So it starts at number 2, and we have a pentene. So that should be the correct name for that one. So there's some common names to remember. So we have things like methylene, vinyl, and allyl. So this is just a reminder of chapter 7, degree of substitution, the number of substituents connected to a double bond. So then we have tetrasubstituted being the most stable, and monosubstituted being the least stable. So then this is about stability. And this is mainly about carbon-carbon chain. So then this carbon, this is a carbon. It's carbon, 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 carbon. So you can see that we technically just take into account carbon-carbon. The carbon-carbons that are attached to a double bond. And this is just a little checkpoint. So it's like classify each of the following alkenes as monosubstituted, disubstituted, trisubstituted, tetrasubstituted. This is just like when it's conceptual checkpoints, it's mainly just like us just trying to grasp a concept. So then, we said that substitution was mainly about the number of carbon-carbon bonds connected to a double bond. So for example, here I have one carbon-carbon, I have two, and then I have three. So then therefore this one will be tri-substituted. Well, let's see, if I look at this one, I only have one carbon-carbon bond. Therefore this one will be mono-substituted. And then here I have 1, 2, and 3. So then therefore this one will be tri-substituted. Okay, so we have addition versus elimination. So then there's some factors to consider. So addition is favored at low temperature, while elimination is favored at high temperatures. And I feel like this is a little bit more easier to consider if you think about what happened on chapter 7. So in chapter 7, remember that at the end of the chapter of SN1 and E1 reactions, I showed you guys a little chart, and I said that SN2 normally happen on room temperature, right? While other reactions, they happen at heat. So for example, if you think about it, what type of reaction happens at heat is E2, E1, SN1. So you can think about it in that way. So those ones happening here. What's E1? What's E2? They're elimination reactions. So then elimination happen in heat. Elimination in high temperatures. While at low temperatures, we have addition reactions. And you can think addition reactions, we are breaking that double bond. You can see we're breaking that double bond, and we're adding components across that double bond. So we first start with hydrohalogenation. So for starters, this is a lot of reactions. I mean, it's not really that hard, but there's a lot of reactions and it's a lot about memory. So what I would advise you is to possibly grab a piece of paper and not like, for example, don't write notes on everything. But I would tell you to possibly just do something. Just do something like, for example, for what we have in there, you know, like, for example, HBr. You know, just to see what happens, and then maybe just take some like little notes. And I feel like, you know, afterwards you're gonna have on your little piece of paper, you're gonna have all the reactions that we're gonna go over, and there's not gonna go any to, you know, just go back and forth throughout the whole chapter and see what a specific reaction you're looking for. Okay, so keeping that in mind, we can begin. So then we have hydrohalogenation. It's addition of a hydrogen and a halide, which you can think about it. Hydrohalogenation is addition of a hydrogen and a halide. So our halides can be chlorine, bromine, or iodine across a double bond, and that's why it's called hydrohalogenation. So we already know addition reactions happen at low temperatures. where they stated that we break that double bond and then we add stuff across the double bond. So you can see on one side we added that hydrogen, and then the other side we added that bromine. So then with hydrohalogenation reactions, we have reduced selectivity. When an alkene is done symmetrically, the placement of hydrogen and halide must be considered. So for example, in here we didn't consider the placement just because in any site, technically it would end up being the same. So for example, if I were to add, the bromine on the other side and then the hydrogen on the other side, they would technically still be the same. Like this thing is the same as this. But in here we have, this is not symmetrical, so it will give out a different product. So in this example, there are two possible positions on which the halide can be positioned at. Reminder, X represents halides. So, when we break that double bond, where would the halide go? Would it go on the left or would it go on the right? So this is when Markovnikov comes. So Markovnikov, he's a scientist and he investigated the addition of hydrogen bromine occurs in alkenes. So he noticed that hydrogens were positioned in the locations that there were more hydrogen atoms. So for example, in here we have a hydrogen, right? So then if we have like an HBr, hydrohalogenations are normally hydrogen bromine, hydrogen chlorine, hydrogen iodine. So then that means that we're gonna add a hydrogen on one side and a bromine on the other, a hydrogen on one side, a chlorine on the other, on one side and iodine on the other. So then when we're doing Markovnikov, he noticed that when we broke that double bond, we added that hydrogen on the side that had hydrogens, or that had more hydrogens. And then he also noticed that halides were positioned on the side of the double bond that was more substituted, or that contained more carbon-carbon bonds. So for example, in here, if you're given this alkene, you can see that in here we have a hidden hydrogen, right? Well, in here we have no hydrogens. So this side, I would add my hydrogen. While in here, it's more, I have more carbon-carbon bonds. I have a total of 2 carbon-carbon bonds. So then we said that my halide is gonna want to go to the position that has more carbon-carbon bonds. So then that's why my bromine, it ends up going to the right side. That is more substituted than going on the left side. So then what's anti-Markovnikov is the process the process that we observed previously is called Markovnikov addition, and it can work for halides like bromine, chlorine, and iodine. But when things like HBr are reacted with alkyl peroxides, we have ROR, in which we get anti-Markovnikov addition. So that's what I mean of doing like little notes. So for example, I would tell you to do a note on this, that when we have HBr with peroxides, ROR is gonna lead to an anti-Markovnikov reaction, meaning that our halide is gonna go on the least substituted, while our hydrogen will go to the more substituted. While in here, when, for example, when this alkene is reacted with only this one, you can notice that in here we have no peroxides, when there's no peroxides present, we do Markovnikov reaction, or we do Markovnikov addition, in which instead of bromine, it does go on the more substituted, and our hydrogen, it goes on the least substituted. So you can see currently we have two reactions. You can also use this one just as for your little notes. Take into account that HBr with antiperoxides leads to an anti-Markovnikov addition, which is efficient for things like HBr but not HCl or HI. So then we have, our alkene, we have HBr, we have Markovnikov. Wow, we have HBr with peroxides, it leads to an anti-Markovnikov. So then draw the expected major product for each of the following reactions. So you can see that the questions, they're not as hard. They're not really that hard. It's mainly about memorizing and getting familiar with the reactions. So I would say we just have to do a lot of practice for this one. And just getting familiar with, with our reagents and seeing what each one does. So, for example, in here, I don't have any peroxides. It's only HI. So, let's see. Let's try to make it as most decent as possible. So then I would put my so if you want to see visually where the hydrogens are, so in here I have one hydrogen, in here I have two hydrogens. We know that our hydrogen, it will go so then we can, in here we can add H and I. So our hydrogen, it will go to the side that has more hydrogens, which will be this one. So we had 2 before, now we have 3 hydrogens. And then my iodine, it would actually go on the side that's more substituted. On one side we don't have any carbons, and then on one side we have 1 carbon, therefore it will go on this side. And this is how my answer, like my final answer, would look like this. So that one goes for Markovnikov addition. Well, in here we have HBr, so that means we're gonna add H and Br, but we have peroxide, so we will get an anti-Markovnikov reaction. So then, for example, let's see. Let me make it nice in here. So then in here I have 1 hydrogen, and then on the other side I don't have any hydrogens. But in here we're doing the opposite. We're not doing Markovnikov, so we're adding our bromine on the side that has more hydrogens. So then my bromine, it will go in here, while I'm gonna add my hydrogen on the more substituted part, which is gonna be this one. And this will give rise to this product right here. So see, it's not that hard after a while. So then you can try it on your own. So draw the expected major products for each of the following reactions. So then in here, luckily both of them, as you can see, they are they don't have any peroxides, meaning we don't have any RI. So then that means that we're just gonna do a Markovnikov addition, meaning that we're gonna add our halide to the most substituted, and then we're gonna add our hydrogen to the least substituted. Okay, so then for the first part, like Alexis said, we can always draw our hydrogen so we feel comfortable with that. If not, we don't need it eventually to draw our hydrogens. So then I would put my bromine on the most substituted part, which would be this one. Remember that we're breaking a double bond and then we're adding our hydrogen on one side and our bromine on one side. That's why we're not showing that double bond anymore. And then, we had originally one, but then we're adding another hydrogen, so we have two in there now. But normally, we already know those hydrogens are there, they're just not shown. And this one will be my product for this one. And the same case goes for the one below. I will put my hydrogen on the least substituted, or the side that has more hydrogens. Therefore, I will put it on. I originally had one, now I have two. And then let's see. So then I would add my bromine or my halide on the most substituted, which should be this part. And again, I already assume that my hydrogens are there, they're just not shown. And that one will be my answer for this one. So I thought about just showing you the mechanism. So this is the mechanism for hydrogenation. So then in here we're not giving any peroxides. So our hydrogen, it went, we first had a proton transfer with our hydrogen going on the least substituted, which will be this side. Therefore, when we broke that bond, we ended up with a positive charge on the other side, and our bromine ended up attacking that other side, doing a nucleophilic attack, and that's why that bromine is positioned on the other side instead. And this is just like the energy chart of what happens. We get a boost of energy due to the proton transfer. Afterwards, we get a boost of energy due to the nucleophilic attack, and when we get our product, our energy goes down. So technically, protonation of addition of hydrogen can happen on any side of the double bond, but when it doesn't react along with peroxides, we prefer to have the addition of the hydrogen on the least substituted and the halogen on the more substituted. So this is technically a little bit more like background information on why we do a Markovnikov addition when there's no peroxides present. So then, conceptual concept. Draw the mechanism for each of the following transformations. Reminding we will begin with a proton transfer, followed by a nucleophilic attack. Without RR is Markovnikov addition. So then it's just gonna be just like this one that we sent. Oops. So then I am just doing like different ways for you. I'm not sure if you technically have to know this, like the mechanisms for this, but I would say so, just because maybe if you do the mechanisms, it's a little bit more easier for you to remember what happens, or why do you get that product. But since this is like an easy mechanism to remember, it will be quite nice to know this for an exam purpose. Okay, so let's see. I might make this one a little bit more smaller so I have more space. Okay, so I have this, I have my arrow, I have my HCl. Okay, so first I begin with my double bond, getting that hydrogen. And then I will put my, since I'm breaking that bond between, I would put that broken bond, those electrons from the broken bond into that chlorine. Remember, we don't have any peroxide, so my hydrogen will go on the least substituted part, leaving this one with a positive charge. Let's see. It will leave that one with a positive charge, and then I will have, here I have my chlorine, which will have negative, and I told you we're breaking that bond and we're putting that creates some electron pairs that are placed on that chlorine. So originally we started with 3, 1, 2, 3, and then we ended up with 4, right? So then we have a negative and then one positive. Therefore we have a nucleophile and then we have an electrophile. We can do a nucleophilic attack, right? And then if we look in here, then we look at this. Let's see. This one already had a hidden hydrogen in here in the first place. Hydrogen, hydrogen, hydrogen. This thing, the same thing as this thing. But you can see that we have our parton transfer and then we have our nucleophilic attack. So you can start on your own now. Okay, perfect. So then we can get started. And as you can see, this is not as, for example, this is not as hard as drawing chairs, right? It's not as hard as drawing Newman. Okay, so first we don't have any peroxide, so that's nice. So then our double bond starts getting that hydrogen. We break that bond, we place it on that bromine. Our hydrogen will go to the least substituted part of that double bond. While our bromine will go to the most substituted part. Let's see. In here we had originally 1, 2. But now we have 3. And then we'll get our carbocation. And then we have bromine, bromine. We have bromine, negative. We can do a nucleophilic attack, right? Now this one will be my product. So, stereochemistry of hydrohalogenation. So then in some cases, hydrohalogenation involves the formation of a chiral center. So then, for example, you can have a double bond. But we add our hydrogen, we get our chlorine, and sometimes out of that, we're gonna create a chiral center. Remember that a chiral center is a carbon with 4 different groups. Some things to consider: two enantiomers produced in equal amounts, it creates a racemic mixture. So what I mean is that, for example, you can see in here that I did a note. If we're chiral, we would technically get the product, and it's an enantiomer. So it's technically like we have 2 products. We have our product, and then plus it's an enantiomer. So then here, like for example, you can say this is my product plus enantiomer, or you can say this is my product and plus enantiomer. Okay, perfect. So then again, we're not doing any peroxides right now, so if you think about it, we'll get something like this. Our hydrogen, it will go on the least substituted, and our iodine will go to the most substituted. Let's see. Oops. Okay. So if you think about like chiral center wise, you would see that, for example, in here I ended up creating a chiral center just because I have a CH3. I have a, in here I have, let's see. In here I have CH2, therefore they're the same, so I can look at the next carbon. Here I have a CH2, but in here I have a carbon. Therefore, I have a different group. So this one's connected to iodine, this one's different group, this one's different, and then this one's different. I ended up creating a chiral center. Meaning that my product, meaning that my product cannot be this one. I have to assign, I have to say that it's a chiral center. So then I could either put my CH3 in a wedge and my iodine on a dash, and then I can also put its enantiomer, which can be iodine, and then CH3. So then that's why it says enantiomer, because it can be any way. And then I would erase this one, and then this one will be my product. So then on a test, technically, they could give you this answer and say this plus enantiomer. So then you know that one will be the right answer. But you could get this one, says plus enantiomer. Okay, so if I was to create this one, I would say first started doing it flat without thinking about chiral centers, and then afterwards you can consider your chiral centers. Another thing to consider is that when doing addition, when doing any type of reactions, technically what gets affected is like the double bond or the things that are interacting with. So for example, this thing, it didn't get affected at all. Well, this thing was the only thing that got affected. So then this part of the molecule stayed just the same. The only thing that got affected is the thing that was reacting. Oops, let's see. So since we considered that, we can add our chlorine, we can add our chlorine to the most substituted, and then we can add our hydrogen to the least substituted. So then if you think about it, technically I wouldn't be making a chiral center, right? Because this one and this one, they're the same group. So then meaning that this one will be my product and my only product. So then I would say when we're doing our notes, if you are doing your notes, I would tell you in hydrohalogenation, if chiral, we will get product plus enantiomer. Like for example, I would put these reagents, H bromine, H iodine, H chlorine. And then if chiral, we'll get a product plus enantiomer. And if not chiral, we only get one product. And then if we do HBr with or HI or HCl with peroxides, we'll get anti-Markovnikov. So that's why I said, like, let's do little notes, because there's a lot to remember. Okay, so in here we'll do this. We will add our bromine on the most substituted and our hydrogen on the least substituted. It will look like this. Let's see if we have any chiral centers. I would say we have one in here, just because in here we have a CH3, in here we have a bromine, in here we have a CH2, CH3, and then in here I have a CH2, CH2, CH3, meaning I have a total of 4 different groups. So I do have a chiral center for this one. So then, let's see. I would put my bromine on a wedge, and then my CH3 on a dash, and then I can do it enantiomers. So in here I will have a CH3 on a wedge, while in here I have a bromine on a dash. So those ones will be my 2 answers, and I can erase this one. Okay, so there's the mechanism for hydrohalogenations. So hydrohalogenations also have carbocation rearrangements. So it is possible to do carbocation rearrangements for these ones. So it's technically kind of the same. So then you can see we begin with our proton transfer, but then afterwards, so then we have our proton transfer. We put our hydrogen on the most substituted. But then if we can go, you can see from secondary to tertiary, if we can go from a secondary to tertiary, then we are gonna do that metal or hydroid shift, and we're gonna make that carbocation tertiary, and then we're gonna do a nucleophilic attack, and then we're gonna prefer that rearrangement product. But that would only so then carbocation rearrangements only happen when it says that we have dilute, so that is something else to consider. So then we can either draw the mechanism, or you can, on your little notes that you're doing right now, you can say this is when we have reagents like dilute HCl. We're technically just doing the same thing, but now we have to consider carbocation rearrangements. On the other ones, we technically didn't consider carbocation, but on this one we do because it's dilute. So then you already technically know how this works. So then we're doing our proton transfer first. Hydrogen, it will go to the least substituted. And then chlorine to the most substituted. So then in here I will get a positive right here. And then, I have my chlorine negative in here. But remember, we can do carbocation rearrangement. When we do carbocation rearrangement, we consider the carbons that are next to that positive charge. So then, technically, if we look at the left side, technically we cannot do anything. Just because, we will get our primary And right now we're sitting at a secondary, so then we cannot make it more stable. We want a tertiary or a resonance stabilized cation for that one. So then I will get, for example, if I were to look at my right side though, and if I were to do, we don't have any hydrogens, right? But we can do a metal shift. So if we were to do a metal shift, we will get a tertiary. So then we could do that. So I could grab this, put it in here. Then I will get a positive in here. And then I could proceed with my nucleophilic attack, right? So now we get this. And it seems like we got our product, right? So then you can draw it on your own, you can draw the mechanism. So then remember, when it's dilute, we can do carbocation rearrangement if possible, of course. So then we have HBr. We're gonna put our hydrogen on the least substituted, monobromine on the more substituted. Let's see, I'll grab this. This one will become positive. I have to see if it's possible to do a carbocation rearrangement. So I have my carbon in here. I couldn't go to the right side because I will get a primary, and I have a secondary currently. But I could technically do 1, 2, 3. I could technically do a hydroid shift, right? On the left side. And if I do a hydroid shift, I could actually get a tertiary. So then if I move that hydrogen in here, let's see, I'll get something like this, and then I can proceed to do my nucleophilic attack, and it would attack this one, and then I will get this as my product. So it's not that hard afterwards. So hopefully you did do a little note. When it's dilute, we can do carbocation rearrangements. Okay, so new one. So we have acid catalyzed hydration. So that one's the addition of hydrogen. So we're gonna add a hydrogen and then an OH across a double bond or pi bond, having OH on the more substituted carbon. So then new note we can add, when we have this rearrangement, we're gonna add the OH on the more. We're gonna add the OH on the more substituted, and then the hydrogen on the least substituted. So then the reagent H3O represents the presence of both H2O and an acid source, such as sulfuric acid. So then that means technically that you're gonna let's see, it's like you can get this reagent, or you can get this one. And so then, for example, you can get an arrow and you can say this, or you can say this, but they will give rise to the same product. So then the rate of an acid catalyzed, is dependent on the starting alkene. The more substituted the alkene, the faster the reaction. So then I just decided to put a little chart. You can see here we don't have any carbons, so then the rate is 1. And here we have 1 carbon, so then it's 10 to the 6. And here we have 2, so it's 10 to the 11, and so on. So then the reaction proceeds via Markovnikov addition. There is strong preference for reactions. For the reaction to proceed via more stable carbocation. So then you can see in here we do it. We have that H3O plus in here. That double bond is gonna steal hydrogen. And then that hydrogen is gonna go to the least substituted. And then, since we took an H from that H3O, we're left with OH, or with water. So that water can attack that positive charge, since it's a nucleophile and an electrophile. And then, when we attack it, that oxygen is gonna have a total of 3 bonds. So then, to make it a little bit more stable, we're gonna remove that extra hydrogen that oxygen has, giving rise to this product. So it's kind of like we're doing proton transfer, nucleophilic attack, and then we're doing a proton transfer. So then equilibrium, reagents, dilute versus concrete. So this is another one that I would take in mind when doing your notes. So when we get dilute H2SO4, or when we get H3O, that's dilute, we get an addition of OH on one side, and then hydrogen. We break that double bond, and then we add OH on the more substituted, and then H on the least substituted. While if it's concrete, it leads to elimination reaction. So then this is a conceptual concept in here. Let's see. So then on the first one, we're adding OH. OH on one side of the alkene, and then H on the other side. I would say that this one's dilute, because we're doing addition. Well, on the one below, we're removing that OH and hydrogen, creating a double bond. Therefore, we're doing elimination, and we're doing concrete or concentrated. So then I would also say you can think about it this way. If we're doing dilute, dilute has to do with water. So in here we're adding water. While concentrated, it doesn't really seem like something that will be fluid. So it'll be like, that could be elimination. But I feel like dilute, that word kind of gives it away, because dilute, I feel personally dilute makes me think of like water, fluid things. So, OH, addition of OH. So then there's stereochemistry, acid catalyzed hydration. So for acid catalyzed hydration, if we create a new chiral center, it will get a racemic mixture suspected. So then it will be the same case scenario. If we get this reagent, or if we get, H2SO4. If it's chiral, when we do that addition across a double bond of OH and H, if we create a chiral center, we'll get the product plus its enantiomer. So then let's see, we can draw the mechanism for this one. Yeah, I was a little lazy on putting up titles. So then most of this ones, we can think about it as H2O plus. It's dilute, so it's gonna be additional water. So then first we're gonna do that proton transfer. Okay, let's see. Our hydrogen, it will go to the least substituted. And then we're gonna have our water, right? Because we took a hydrogen from our H3O plus. So then in here we have some electrons that can react with that positive carbocation. So then water already has 2 bonds, right? So then when we're attacking it, we create a new bond. So then that means that we could technically remove an extra hydrogen from our product. And then this will give rise to this product. So then we follow that pattern of proton transfer, nucleophilic attack, and then proton transfer again. And again, we use the same logic for this one. So, there's so many different ways you can memorize things. You can memorize how they work. The OH is gonna go, to the more substituted. And then the H is gonna go to the least substituted, or you can draw mechanisms. Personally, when I did OChem 2, I, because you're gonna have a thousand, like, there were times when I was taking an exam and I had like, it's pretty easy when you're doing, like just 10 reactions, but I will have like 30 reactions. So knowing the mechanisms was pretty helpful for me in the long run. Just because, if you knew how to draw them and understood what's going on, if you understood the patterns, then you could eventually just draw the mechanisms. So if drawing the mechanisms makes it a little bit much easier for you, then I would say do that. But if memorizing works better for you, then just do that. I always say, everyone has a different approach to OChem. You just have to find what works best for you. Okay, so then with that little note in there, we can do a proton transfer. So then H and the least substituted. I can proceed to the nucleophilic attack. I could remove that hydrogen, and I will give rise to this product. Okay, perfect. So then you can draw the mechanism for this one. And I think afterwards, I don't really show that many mechanisms. Or I don't really ask you because they do get a little bit more complicated. So I feel like those ones are the easier ones, which are more probably to get on a test rather than the other ones. Okay, so draw the mechanism for the following reactions. Okay, perfect. So I take a hydrogen from there. I know that my hydrogen will go on the least substituted. And then I can use that water to do my nucleophilic attack. And then my oxygen will have an extra hydrogen. So then I can just remove it. And that one will give rise to the product. See? So after a while, it just comes naturally. So next reaction. This is another method to achieve a mechanical addition of water across an alkene without carbocation rearrangements. This method is called oxymercuration demercuration. So I did put out the mechanism, but you're not expected to know how to draw this big thing, so don't get overwhelmed. So this is the whole mechanism of how it works. So it's kind of like they're together, and it kind of like pops open, giving rise to this. So then, okay, so just to make it easier, this is the overall reaction. So then the net result is the addition of hydrogen and a nucleophile across an alkene. The overall results in the mechanical addition of OH and H across a double bond, OH on the more substituted, and then H on the least substituted. So then I would say add this one to your little notes that you're doing currently, if you're doing them. So then if you get this reagent, you get your nucleophile on one side, and then your hydrogen on another side. It says nucleophile technically because in some cases, this thing can change. But basically, it's this what you have to be aware of. So then when you do your notes, I will put all of these ones, but it's mainly that you have to consider that this thing can change. Like, you're gonna get the same result, but then, you're like this one, it won't be an OH, it will be something else different. But it will still, like, this thing will go on the more substituted and hydrogen on the least substituted. So when you get this reagent, you will get your nucleophile on the more substituted and then hydrogen on the least substituted. And there will be no rearrangements. So when you get those reagents, OH or your nucleophile, the more substituted, hydrogen on the least substituted, and then you have to keep in mind that there will be no carbocation rearrangements. So then I feel like this one, it can be a little bit tricky because it was asking us to do like two different, it was like combining like two topics at once, and I don't want that. So then we're just gonna do this. Instead of two different products, let's just focus on the reaction that we learned. I don't want us to get confused. So what do we learn? So what we learned is that if we get these reagents, our nucleophile, it will go on the more substituted, right? On the or hydrogen on the least substituted. And what's nice is that we don't have to focus, or we don't have to worry that there will be carbocation rearrangements, because there won't be. So then my OH, it will go in here, and then my hydrogen will go on the least substituted, because in here I have two hydrogens and in here I have one hydrogen. Therefore, my hydrogen will go where the most hydrogens are. And this one will be my product. Okay, perfect. And then again, my OH on the more substituted. And then my hydrogen on the least substituted. Taking in mind that in here I have one hydrogen, here I have two. I'll put my hydrogen where the most hydrogens are, and my OH on where the most carbon-carbon bonds are. So once again, when you do your notes, put in big bold letters, no carbocation rearrangements. So with that in mind, we do a new reaction, which is called hydroboration oxidation. This method is to achieve an anti-Markovnikov of addition of water, meaning that your OH group goes on the least substituted position. So when you get these reagents, your OH will go on the least substituted, and your hydrogen will go on the more substituted. So then, again, when you do your notes, it's when you get this reagent. So I would say, like this chapter, think about, you have this thing on a flask, and then you throw this thing over it. What happens? It's kind of like that. So that if I got this thing on my flask and then I throw this, it's not gonna give me the same thing if I were to throw this instead. So, stereochemistry of hydroboration oxidation. So for this method, it's preferred for hydrogen and OH on the pi bond to face the same direction. In the book and throughout the rest of the semester, this is referred as zinc addition. So then again, in this one, we do an OH and H addition across the double bond, with our OH on the least substituted and our hydrogen on the more substituted. The thing that we have to keep in mind when I mean zinc addition is that if we are, let's say, if we are creating like chiral centers, or most of the time, we have to consider stereochemistry. We're gonna add our hydrogen and our OH are gonna be added as wedge and wedge or dash and dash. So you can see that both, they were added as wedges, or that they both were added as dashes. So then, therefore, in here, these ones, they're not achieved. So then the ones below are not achieved because for this type of reaction, it only happens on wedge or dash relationship. Those are the only answers we can get. So that this one is a wedge and dash, so then it doesn't happen. Dash and wedge doesn't happen. We only want zinc addition for this one. So when you do your notes, I would say we are adding them to wedge and wedge or dash and dash. Wedge or dash relationship. Zinc addition. And this is just the mechanism for it. You don't need to know it, but it might be helpful to just have an idea of it. Because look at that. I don't think you want to draw this on a test. So this one will be the oxidation, proton transfer, nucleophilic attack, rearrangements, proceeds to nucleophilic attack, a loss of a living group, and then proton transfer. So I don't think I'll exist that mean to make you guys memorize this. So then overall, hydroboration oxidation is anti-Markovnikov addition of OH and H if there's stereochemistry, Make sure that they face the same directions, dash dash or wedge wedge. No need to memorize the mechanisms. It's nice to have an idea on how they work since there are so many reactions, therefore it could be helpful to be able to differentiate them. So then conceptual concepts, rather products of hydroboration oxidation reactions. And remember, like I said, if chiral, we add them like that. If not chiral, we don't really need to add them like that. So then in this case, we're gonna do an addition of OH and H across a double bond. H is in the more substituted and OH in the least substituted. So remember, that's what happens when you get those reagents. So then let's see, I'll get this. Oh, sorry. I'll get this. My OH, it goes on the least substituted. And then my H on the more substituted, which will be this one. The same logic goes for the one below, in which I will put my OH on the least substituted and my H on the more substituted. And this one will be my final answer. So then, specificity of hydroboration oxidation. As we know, in this method of water addition, we do syn addition, meaning what we said, wedge or dash dash. But we need to consider if we're creating a chiral center or not. If there are no chiral center, then specificity is not relevant. Just like in here, it's not relevant. But if there's one chiral center, we get both enantiomers. So then, if there are two chiral centers, we need to remember that we're doing syn addition, and that will get a pair of enantiomers from that. Remember, syn addition means wedge or dash dash relationship with your OH and H. So for example, you can see that we have two chiral centers, but since we're, we cannot do, our product cannot be, OH. If we add OH and H, they cannot be, we add OH as a wedge and then H as a dash. They both have to be on wedges or they both have to be in dashes. So then let's practice. Okay, predict the products for each of the following transformations. And let's see. OH on the least substituted. And then H on the more substituted. But that is, of course, if we have chiral centers and none. So you can try it on your own. So like I always recommend, I would say just try to draw them flat first and then see if you get any chiral centers from it or not. If you do, then we have to consider stereochemistry. So then OH, it will go on the least substituted, and then RH on the more substituted. So then if you think about it, technically we are creating a chiral center in here. So then therefore, since we're creating a chiral center, we are gonna have to specify our wedge or dash and dash relationship. So then remember, we have to add them both on wedge wedge or dash dash in this case. So then I would add my hydrogen, and then meaning that this one will be on a dash, and then I will have to put its enantiomer, meaning I will have my OH on a dash, this one on a dash as well, this one on a wedge. So then catalytic hydrogenation, it involves addition of molecular hydrogen H2 across a double bond in the presence of a metal catalyst. So then this one's pretty straightforward, right? H2 PT, we're just adding hydrogen on one side and hydrogen on another side. So stereospecificity of catalytic hydrogenation, not all products are observed, so we only get syn addition. We only get syn addition again, meaning we only have wedge wedge or dash dash relationship. So if we were to create chiral centers with this, which in this case we do, you can see that for example, our hydrogens, they were added by syn addition. That's why these ones were either, they were either dashes, like this one, and then we get its enantiomer. And that's why, since we can only do syn addition, that's why we don't get these products. In this example, we'll have meso compound, therefore there's no enantiomer form. So then we do have to consider things like meso. Meso, remember, is when we get wedge and wedge, so on the same side, and then there's a line of symmetry, therefore this molecule and this molecule will be the same, so technically it will produce, syn addition produces only one product, so it will be a meso compound, which would be this one. It could technically, the answer be this one. It could also be this one as well, but only one of them, not the two of them. So then let's practice. Predict the product for each of the following reactions. Okay, so then we're just adding hydrogens on both sides. First, you can see I always draw them flat. And then if you think about it, in here I technically don't have a chiral center, so I wouldn't really bother on drawing that one. But in here I did create a chiral center, so I would draw that I added it as a, and that I added it. But since we're not, this one is not a chiral center, I would technically wouldn't show where is a wedge or dash. So then let's see, I'll get this one and I'll get this one. But I mean, if you really want to, I can always show, just for purposes that we're doing that syn addition. And then I will add my hydrogen, then this one, and then I'll have my hydrogen in here. So just syn addition. So then you can try it on your own. So you're very lucky. So then in this example, for example, this one and this one, they're the same. And then this one and this one are the same. So technically you wouldn't have to really worry about stereochemistry. You just have to focus on the overall reaction, which is just adding hydrogen on both sides. This would eventually lead to you on getting something like this. If you really wanted to show stereochemistry, you get this and this, or this and this. I just wanted to show that we're doing that same addition. But since technically it's not really chiral, that answer will be wrong. So I do want to show that this one will be the correct answer. So what are PT, PD, and Ni? They are heterogeneous catalysts. They do not dissolve in the reaction medium. With a homogeneous catalyst, acid addition is also observed. So you can technically see that there's not really a difference. We're still doing, we're doing that syn addition of hydrogens. We're still adding those hydrogens on a wedge or dash relationship across a double bond. So you also have a halogenation, which is an addition of, or halides, either bromine 2 or chlorine 2 across an alkene. So you can see that across a double bond, we just broke that double bond and we added chlorine or bromine. Halogenation reactions are formed in an anti-addition. So we see syn addition, which is, wedge and wedge or dash and dash relationship. But in this case, we do anti-addition. So then when you do your notes about halogenation, just remember to specify anti-addition, meaning that we're getting a wedge and dash or dash and wedge relationship. So you can see in here we have this alkene with cycloalkene, and then we have bromine too. So then you can see that on one side of bromine was added as a wedge, on the other side was added as a dash, and as always we get its enantiomer as well. So this is kind of like the mechanism. You don't really have to know it. So then conceptual checkpoint: predict the major products for each of the following. For each of the following reactions. So I feel like in this case, I would indeed show stereochemistry for this one. So then we're doing, on one side our bromine will be added as a wedge. Then on the other side, let me break that double bond first, right? And then on the other side we added as a dash. Therefore my CH3 from here will be in a wedge. Then my CH3 in here will be in a dash. And then I will get its enantiomer, which is basically this one. Okay, so you can try it on your own, and you can predict the major product for each of the following reactions. So then this one is a little bit easier. It's not really easier, but you don't really have to worry about the CH3, I just wanted you to be able to do this one and then see that we're doing that syn addition, So then that you're able to see that in here, we're adding a bromine on a wedge, and then on the other we're adding a bromine on a dash, and then we're getting its enantiomer. And then the enantiomer, it will technically be this one, the top one on a dash, and then the bottom one on a wedge. And then we have halohydrin formation. So then this reaction is the addition of that halide on one side and then an OH on another side. This is called bromohydrin, and then addition of chlorine and OH across an alkene is called chlorohydrin. Halohydrin formation reactions are reuse selective, meaning the OH group is on the more substituted, while the halogen is on the least substituted. So things to know. OH goes on the more substituted, and then this reaction is also an anti-addition. So that means that we're adding that OH on a wedge and then that bromine on a dash, or we're adding that OH on a dash and then we're adding that bromine on a wedge. So I would personally draw this on my little notes and just put, oh, remember we're doing anti-addition, wedge dash or dash wedge, and then OH on more substituted, and then my halide is gonna go on the least substituted. Okay, perfect. And then they want this one to be reacted with bromine 2, H2O. And then we have to remember that we're doing bromine and OH addition. So then let's see. And then we're adding our OH on the more substituted, therefore it will go this way. And then I would add my bromine on the least substituted, which will go this way. This one has 2 hydrogens, therefore I don't really need to worry about the stereochemistry for this one, but then this one I will get a chiral center indeed. So then I will have to worry about that one. So then let's see, I'll get this. I'll put my OH in a wedge, and then I'll get my enantiomer, which will be this one. And just for purposes, if you want it, you can say, oh, I added my OH on a wedge, then I added this one on a dash, and then my OH on a wedge, and this one is on a dash. No, it's on a wedge. So then now you can try it on your own. And I do feel like for this one, you're gonna have to specify the stereochemistry for this one. So then remember, we're gonna put our OH on the more substituted, or we're gonna put our halogen on the least substituted. So in this one, I'm gonna put my bromine on a wedge. So then I'm gonna add my OH on a dash. And then I'm gonna put, since we're doing, we're assigning wedge and dashes, this one is gonna go on a wedge. And then I'm gonna draw its enantiomer. So I'm gonna put that bromine on a dash. This one is gonna go on a dash, and this one's gonna go on a wedge. And then anti-dehydroxylation. So reactions that are characterized by the addition of OH and OH across an alkene. So you can see we're just adding OH on one side and another OH on the other side. For this type of reactions, we will use the following reagents. It should be this one and this one. or in a much nicer way, these ones will be the reagents. So then predict the major product for the following reagents. Some things to remember. These reagents give an OH additional across an alkene. And we need to have a wedge dash or dash wedge relationship. For example, in this one, you can visually see that we're gonna be creating chiral centers, right? So then, for example, on this side, I'm gonna put this one on a dash. Therefore, my OH is gonna be on a wedge. So then, meaning since we have to do wedge and dash relationship, my other OH is gonna be added as a dash. And then I would just have to draw its enantiomer, which will be this one. And then you can try it on your own.
¿Ya salió?
Okay, so since we're gonna add OH on one side and OH on the other side, and then you have to consider wedge and dash relationship. You don't really have to specify if it's not a chiral center or not. So then here will be like this, and then it will be like this if it was flat. You can see that in here I don't really create a chiral center, but in here technically I would, so I would majorly specify wedge or dash on that one, which it does make it a lot easier eventually, because you know you can just say this. And that will be my answer. But remember, if you wanted to really specify, this one will be in a dash and this one will be in a wedge, just because we have to do anti-addition. So then, since dehydroxylation, this reaction is the reaction in which there is an OH and OH addition across an alkene. The following reagents provide a syn addition of wedge and wedge relationship. So then, meaning if we were to get these reagents, so then I would also put this on your notes. If you were to get these reagents right here, specifically this one, I will get instead of an anti, I will get a syn addition, which be wedge and wedge. Okay, perfect. So then let's see. In here I got so if I were to just draw it flat, you know, I will get OH and then with OH. But the thing is, like on the previous problem, in here technically we don't have a chiral center. In here we do. So therefore, I would just need to specify technically chirality or wedge and dash relationship. But that one which is kind of nice. But we do have to keep in mind that this is like a sin when we get this type of reagents. So make sure to put that in your notes that we have to do a sin addition. And then we're gonna draw its enantiomer. And that one will be my answer. So then let's see. So for this one, it is quite nice because in here we are actually able to see that that sin addition. So then remember we're doing an OH addition. And then remember we want wedge or dash relationship. So then we're gonna add that. And that will be my answer for those two. So then this one's pretty nice actually. It's called oxidative cleavage. This reaction is called an ozonolysis reaction. So then ozonolysis only happens when we get these products down here. So it's technically pretty easy. So you can see in here we're kind of like breaking double bonds technically. So if I were to break this one, I just draw, you know, an oxygen between that double bond and then another oxygen. And you can see that this created this and then this created this. And which is kind of like a little bit different when we have you know, a cyclo, because we do break it and then we end up doing this but then instead, you know, we're gonna have them still being connected together. You know, they're still connected. Like in here I have 1 carbon, in here I have 2, in here I have 3, in here I have 4, here I have 5, and then here I have 6. So you can see I have my double bond oxygen and then here I have my end. So it's technically like it's still the cyclo, but we just broke it open. It's the same thing. We're just breaking double bonds and then doing double bond oxygens instead. So from 1 double bond, we're creating 2 double bonds oxygens. So then practice the skill. Predict the products that are expected when each of the following compounds is treated with an ozone following by DMS. So when we're treating this one, we're just gonna be breaking those double bonds and then we're gonna be creating double bond oxygen, double bond oxygen, double bond oxygen, double bond oxygen. Remember, these ones are connected together. We're just gonna be breaking the double bonds. So that one will be my final answer for this one. And then again, if you try it on your own, predict the products that are expected when each of the following compounds treated with an ozone following by DMS. Again, we're gonna have our same reagents. We're gonna be breaking this one, double bond oxygen, double bond oxygen. We also have to remember to break this one, double bond oxygen, double bond oxygen. And remember, these ones are still connected. This one is just hanging on the air. So then let's see, I would get something like this. Let me make them a little bit more separated. Okay, perfect. And then I will get this. And that should be all the reactions for this chapter. And if you actually want, so some people, they do want extra practice problems. I cannot recommend, sorry. So I cannot recommend this teacher enough. So then if you do this, if you do MSUM, and then you do Jasper's organic chemistry, and then you do fall online. This teacher, he was my teacher for OChem too, and he actually posts all his class online, which is quite nice. And you can just search for throughout his test, and he has like lots of practice problems for this type of questions. So if you really want like extra practice, I would really recommend you to go through it. You can click the link, and then you can click just test, and then you can get the answers as well. And you can also get, it says movie, but it's just a video of him solving the problems. So it is quite nice. So if you want some extra practice for maybe the exam or even the final, I feel like he's a pretty good source for it. So that should be everything for today. And soon enough, either by the end of this week, I should have the exam 3 review up. So hopefully this is able to help you guys with chapter 8. And I hope you have a wonderful night.